All right, welcome back, folks. Our next item is to read this paper in a continued exploration of prompting. We are going to do this pretty important concept. It's a relatively recent paper, the V2, but it sort of came towards the second half of 2023. Now, are you folks able to see my screen?
Yes, we can.
And what this paper needs some background actually to grasp what it is trying to say. One thing it needed was the chain of thought. So let us first recapitulate what we did in chain of thought. You ask a language model to do some things that's a little hard for the language model. Like you give it a word puzzle, right? That Mary bought 26 apples, gave 6 to the neighbor, received 2 from another neighbor, and so on and so forth. 8 of 5, and the family 8 of 5. How many apples remain? So when you give it, what happens with language models is you're looking for a number. To a language model, quite often, one number looks as likely as the other. So it will just emit out a number. And as far as it is thinking, it's doing a pretty good job. It just produced out a small number. It produced a number rather than some gibberish, some word like lion or something like that. But so in a way, it's pretty close, but it's not the right answer in mathematics. Precision, exactness is necessary. It's not exact. So one way you can impose exactness, which is required in logical reasoning and in arithmetic problems, is or just sort of guide it. You feel that it has landed. One intuition that I have is you ask it to go right to some place, like let's say visit your house, but somebody is wandering around the playfield in your neighborhood, right? Reach that far, which is a pretty good achievement, but you need to give further guidance. And so the chain of thought was the core concept was to guide it on how to reason, but actually not reason, but to give it how to give a few exemplars, and so it can repeat a reasoning along those exemplars. Are we together? And as it repeats the reasoning or a pattern, it sees a pattern in the exemplar, it is far more likely to stumble upon the right answer. It doesn't always stumble upon the right answer. So COT, this is often abbreviated as COT, is not foolproof, but it does seem to help in quite a few situations. And it does bring about a substantive improvement over standard prompting for many, many situations. So, and COT is another illustration of the fact that do give examples, and good examples have a theme that we have been harping on for quite some time. Now, once you take the COT, there are further insights we can draw. Like how do you take it any further from there, and what's the next level of development, which is the COT. So it's usually written like that: self-consistency with self-consistency check. You can augment COT thinking or technique with another thing called self-consistency added to it. And I'll first start by explaining that. In the portal, I've added the research paper for COT with a self-consistency. But because of this paucity of time, I will cover this paper in greater detail because it represents a big milestone. And along the way, I'll introduce the idea of COT with self-consistency. So the best way to do that is to say this. See, a large language model, at the end of the day, is a causal, it's an autoregressive or causal decoder that given the input prompt, and whatever system instruction you put, so all of it being the input. So you take the user input, let's say, let us create some terminology. Suppose you have the user input, right? You augment it with your system prompt, whatever prompts you have. And so this goes to, let me just call it the prompt of X. So prompt of X is not necessarily what the user input, but it's further decoration with whatever system prompts that you have given and other examples, etc., that you may have given. Are we together? So this becomes your real input. It goes into the language model, LLM, and then the moment you do this, the first token comes out, right? Let's say that Y1, Y2, YK have come out. Now, let me ask this question. This is just a quick review. YK plus 1, which token next comes out? The probability of the next token, of picking the next token from a dictionary of words, dictionary of tokens. What does this probability depend upon? It depends upon, what all things does it depend upon? Does it depend only on X? Is this the value, or should we say no, it depends also on the system prompt that you wrote? It also depends upon the prompt with which you augmented the initial user input. Does it depend only on this, or it depends on something else also? It depends on not this, but one more thing. The previous things that it has produced, YK plus 1, is conditioned on the prompt of X and Y1 all the way to YK. Isn't it? Are we together? The previously generated tokens. Now comes an interesting thing. What happens is that you get a softmax, right? Suppose you have a dictionary with M things, you will get softmax probabilities for each of the tokens, TI, right? You're producing this. Now what happens is, and then remember, there is something else dialing in and dialing the softmax up and down. What is that parameter? The temperature, right? It determines how likely you're to choose the most probable, the highest probability token, right? Because you sample off the softmax. When you sample off the softmax, what happens is that it becomes a non-deterministic machine. And so when you produce one token and next token and the next token, you get an answer. It is one of the many answers the LLM could have produced. You try it again and you'll get a different answer. Does that make sense? And you try it again and you get a different answer. This is the nature of a LLM. You can try that. You give it a prompt, you get an answer, then you try it again and you get a different answer. Right? But hopefully meaning exactly the same thing, having essentially similar semantic content. Yeah. You do that. Or if you're doing creative writing, then you do want diversity and you want different things to come out. But in the case of arithmetic reasoning, what do you want? You know that it is sampling off the softmax. So you try it again, it will produce a different answer. You try it again, you produce a different answer. But Mary and her apples, there is a unique answer, isn't it? So what will happen is a number is popping out every time. How many apples remain? Now, if you keep repeating this, what will happen? Sometimes, let's say that the correct answer is 42, right? So 42 may come out. Sometimes a wrong answer may come out, isn't it? Despite your chain of thoughts. Let's say 25 came out, something, etc. 42 came out, right? So what should be true if your prompting is correct, if your exemplars are good, right? What should be true as you keep repeating this with the same prompt and the chain of thought? If you keep on repeating with the LLM, what should be true?
You should get the same output over and over again.
You should get it majority of the times, isn't it? Occasionally it will make mistakes or produce something else, but it's almost like the right answer is spinning it down, like things are moving towards it, sometimes in the neighborhood of that or not, right? So if you take the majority vote and pick the majority answer by repeating it by multiple tries, you should hit upon, you should say, okay, Mary has 42 apples. No, not really. You just say, okay, yeah, you can talk about how often it came up with the right answer, right? And people do look at it, but generally, it does tend to work occasionally. So that is the idea here, guys. So let's look at this diagram, which is sort of for the tree of thought world. This is an iconic, sort of like it's a famous picture. It's supposed to convey the entire thing, right? So a standard prompting is what? You give a word puzzle. From the word puzzle, you get an output. Some number may come out, 23. Right? Now, from experience, empirical evidence says straightforward input-output prompting does not lead to as good results, does not lead to robust results, isn't it? Now, you brought in chain of thought. That's what we learned the last time. It is much more likely to be right, but you realize that it's not guaranteed to be right. It's never guaranteed to be right. A chain of thought is just one path of reasoning that the machine took from the many, many paths of reasoning that it could have taken, isn't it? Many, many outputs that it could have produced. It just happens to be one path. Yeah. And so you may still have errors here. Now, the self-consistency with COT, that's why it's written COT SC, it just says that take different paths, like you can go by this path, you can go by this path, you can go by this path, any one of the complete path. At the end of it, take the majority vote. That's the basic idea, right? And empirically, it turns out that it does work. It does better than just pure chain of thoughts, just like pure chain of thought works better than just input-output prompting, especially for this class of problems. So this paper actually extends it significantly further. Right? What it does is, and I'll give you the core idea, which I think the author says, but I'll slightly change the emphasis and say it differently. Now, in machine learning, in AI, there is a concept of exploration versus exploitation. In fact, you also learn about it in business school. Right? Krishna and I are familiar with that. Right? We went through a whole section of it, week of it. So, what is exploration versus exploitation? Who would like to mention that? What is exploration versus exploitation in AI? I'll give you an illustration since no one is giving me. But see, suppose you have, imagine a colony of bees, right? Now, there are different flower beds in the neighborhood from which you can go gather your nectar, right? The bees go out, they have no idea where the flower beds are. So one bee is buzzing around and hits upon a flower bed, right? Or seems to be sensing that there's a flower bed there and pursues that direction. Do you think all the bees should just go straight to that? Because that bee will now start signaling, I found a flower bed. Is that a good idea? Is that the best idea? That the entire bee colony should go to that flower bed? Why is that not a good idea?
I will take the honey.
What's that?
I'll steal the honey.
Overexploitation is a single answer.
Oh,
Say that again?
Overexploitation is a single answer.
Yeah. Over exploitation of a single answer, yes. No, but what is it in terms of this picture, this story, or what should the bees have done?
The bees should have independently explored and come and share their results. And the others should be free to go and follow those paths, whichever they choose.
Right. See, what happens is when you go on to the first answer that makes sense, it's a greedy approach, right? You go into exploitation mode. Okay, we found something. Let's go get it. The trouble is, it may not, that flower bed may be a tiny flower bed, isn't it?
there may be another one bigger.
There may be a better flower bed, much bigger flower bed. There may be many big flower beds. Are we together? So you should always balance exploration versus exploitation. And this is very real world. Like, as I said in the example of the bee, this also applies to companies. Like, for example, in business school, we are taught that one strategy is, like, when you say keep enhancing the product. Most mature companies, what do? They have a product. Product managers go out, they come back with more enhancement requests. And the engineering team just keeps on doing that. It's a very comfortable life. Yeah. Product managers have it easy. All they have to do is go to the customers and say, what do you want next? And customers say, wow, he's actually asking me. I want this, I want this, I want this, right? And soon you get locked in. In fact, in the world of business, there is a book, it's called The Innovator's Dilemma. Why is it that companies that innovate ultimately become dinosaurs? And part of it is that they keep listening to their customers all the time, and the customers box them in, right? So it is all about exploitation and not exploration of the other greener pastures out there. The world is changing, new opportunities are emerging, and they are not exploring. Are we together? And so that's the innovator's dilemma. So the same problem here. Now that's a big context between exploration and exploitation. In AI, the first thing that you learn in a textbook is one of the first things is that you need to balance exploration versus exploitation. Because there is a possibility that the first hit that you get may be the best one, right? But there is a non-zero probability that there may be even better hits out there, isn't it? So you have to balance exploration versus, and if you ever study the bees, you will see that they do it. What happens is that if a bee is going this way and she hears the hum, signaling that there is something out here, they don't completely go there. They actually slightly move there. Some of them will go there actually, and the rest will continue their exploration. And they apparently signal how strong the flower bed is. That adds to the thing. And actually, one of the papers that we wrote in 2012, 2013 with Dilip, who is in this audience, was literally that. How do you do nano delivery? Use nanobots to deliver cancer drugs. Those bots will get dissolved and get lost in the human body. So we literally use the example of the bees to do sort of a balancing between exploitation and exploration in that. So, because what we had to deliver is this, for cancer cells, or for that, the payload would be the toxin that would kill the cancer cell. And they could take it out and so forth. So anyway, that was long ago. Now, from that lens, if you look at this problem, you realize that chain of thought is great, but what is its flaw? No, it thinks sequentially. One line of thought that it takes, it just goes straight along that. It's pure exploitation. If the answer is good, good luck. If it isn't, hard luck. Right? That's how it is. On the other hand, if you look at the self-consistency with chain of thought, what do? You say, well, let's try many, many paths. But the problem with that is you have to run many trials, lots and lots of trials before you get there, right? And then take the majority vote, right? So no one path is benefiting from the, from the reasoning done by other, right? The thinking steps. See, there may be a thinking gem. One guy may have thought of just the most brilliant idea here, right? And another line may have thought about the most brilliant idea here, let us say, in this part, right? So one path may have thought the first part of the first step really well, but after that made just bad decisions, right? Somebody else may have thought the second step really well with the poor first step, but after that gotten lost or something like that. I'm just giving an analogy. And none of them may have gone to the right answer. But it is possible that the right answer is when you have all of these right thoughts happening at the same time. Right? So the question is, can you do that? Can you think lots of thoughts and then have a way to cherry pick the best at each step in the chain of thought? Right? So let's say that let's hardwire it. Let's say that you need 3 steps to come to the right answer. Theoretically, to simplify the problem, just assume that you need 3 steps. So can I first pick the best first step, the best second step, best third step, and get to the answer? That would be the optimal way, isn't it? Right? But how do we do that? Now that requires a little bit of a graph theory thing. And 2 concepts I'll just go back and review. I'll just review a few words, and you have to tell me how much you guys remember it, or whether I need to review it at all. They are words like, and most of you will, but I want to just spend. Why am I spelling it wrong? BREADTH, is this correct? Okay. First search. And depth first search. DFS, yeah, DFS, exactly. And then backtracking, and look aheads. Opposite of it is look ahead. Just look a few steps ahead. What will happen? Okay. So to illustrate look ahead, what happens when you turn your headlight off and drive a car in the dark? You just lose the look ahead. As literally that. Look ahead is just being able to see a few steps, a distance that you're going, that you will be there in the next few steps. Right? That is simply look ahead. Right? And backtracking is just knowing that that's a wrong path and coming back. Right? Are we together? Right? If you know that that's not a good way. So for example, a bee finds out that there is nothing in that direction. After a few trees, it's just desert and more desert. So what should the bee do? The bee should backtrack a few steps, isn't it? Till the bee is back into forest or gardens. That is backtracking. Breadth first search and depth first search, I'll mention it to you, what it is. Anybody, should I give a 1-minute review, or is it patently clear to all of us? Should give a quick review. Yeah. So imagine that you have a graph. You are here. You could go here, you could go here, you could go here. From here, you could go here, right? From here, you could go here, maybe here, maybe here. Let's say from here, you could go here, and here, and here, right? And here, and here, and so on and so forth. Suppose breadth first search is saying this. Suppose you start at A, right? You first visit each of your nearest neighbors. Are we together? You visit your nearest neighbors and find who they are. So you create a list. So the way you do that is, people imagine that you have a long queue. So the way I like to think about it is that this is your buffet queue. Who gets to eat first? Right? So buffet queue. Food. Right? So the first node, first of all, A is put here. Let me just put B, C, D, E, F, G, H, I, J, K. So in the beginning, you get A in the queue. Right? You start at A. So A has had food. Are we together? So when A has had food, now A is asked, okay, who next? So you ask A. So A reaches out to the nearest neighbors and puts them in the queue. It says B, in no particular order, B, C, D, or it doesn't matter. It may in random order put its neighbors into the queue. All right. So now what will happen? A is done with eating, so B gets the plate. B, at that particular moment, what does B get to do? B eats and is asked, who are your neighbors? What can B answer? E, F, G, let me mark this as G, H, I, J, K, L. B will say L and F. Does that make sense, guys? B will say that. So B is gone. Then C is going to eat. Then C is going to ask, C is going to report on the nearest neighbor. F is already in the queue. You ignore it. Then it will be G and E. G, E. Does that make sense? Do you see how it goes? Right? So if you see it, the way to see it is that it's breadth first search. It's like a ripple going out. It's like if you imagine that you have dropped in a lake, a pebble at A, the pebble is going and hitting B, C, D first, the first neighbors. It's a wavefront, it's a broad wavefront. The ripple is hitting B, C, D first. Then that, if you notice that, what is the next thing that happened? It went and hit the next layer first after that. And they are quite literally, if you notice, they're often two hops away from this, isn't it? And then the next wave will pick some things up, and then next wave will pick this. So it's like a ripple moving forward, right? This is the breadth first search, BFS. Breadth first search, because literally it's a broad exploration of the nodes. It's like a wavefront going and hitting the different nodes.
It's like fungal growth.
It's like a fungal growth, yes. Says the surgeon and doctor.
Fungus growth like that. And
Yes.
then they find the optimal paths. of
That's
method.
right.
Yeah?
Yes, that is true. What is the depth first search? Depth first search is the opposite, right? Depth first search is, how should I do that? It is like a stack. What you do is, imagine that you're going for the plates. Each of these things are plates. Right. Actually, I should not use this. Let me use this itself, color, and it's a stack. First, you put A, right? And then A is done, and in no particular order, A will put B, C, D. All right? These orders is not matters. B, C, D could be jumbled up, but they are the immediate neighbors. But now what happens? You can only, the guy who gets to eat the food is the one at the top of the stack. So who would that guy be? D. So you go to D, and D eats food, but when D is done, what is D going to bring to the party? D can only bring C, but C is already there. So D can bring E, isn't it? So D can bring E. There you go. And then you ask, actually, I made this wavefront. I should remove this wavefront here. Now E is asked, hey, now that you are done, who do you bring to the table?
C.
Well, C is already there in the queue. You have nobody else to bring, right? So at that moment, effectively, a backtracking takes place, right? What happens is you have to go back to C. The next guy on the top is C, isn't it? So you go to C, feed C. Now, when you have fed C, who does C bring to the party? E is already done. C can bring F and G, isn't it? So F and G come to the party. Who is at the top? G. So G now finishes the meal and asked, who do you bring to the party? Says I, H, in no particular order. And then who is at the top? H gets to eat. When H eats, who does H bring to the party? Right? J, K, right? J, K. Right? So now look at this, and then maybe a K gets to eat. Now look at the sequence of people who got to eat. A got to eat. Let me shrink it a little bit. Yeah. A got to eat. Who else got to eat? C got to eat. Right? D got to eat. E got to eat. But G got to eat. H got to eat, and K got to eat. So you realize that it is like, if you look at the paths here, you tend to go successive layers much faster, isn't it? At the expense of ignoring a lot of things which were much closer to A. Right? So it is a depth first search. Right? It is more, it's not a wave front rippling from A. It is more like you have taken a big drill and you're drilling into the earth. Right? Going as deep as possible, as quickly as possible.
So as the path there from A to K, it doesn't, let's say it finds K and realizes it's wrong. Does it
Then it has to backtrack.
does it go from A to J now?
Yeah, so then it will backtrack. So that's a very good question. So what is backtracking? Let's say that you reach K, but K, like now I'm going to change the metaphor. I'm going to say it's about flower bed, location to location. K is a desert. Then what should the bee do? They knew, let us say that it knew that up to H was fine. Then it should go and check J, isn't it? But if it turns out even H was not fine, then it should backtrack here and try other paths, isn't it? So that is the backtracking aspect of it. Are we making sense? Right? That is it. So that is the concept of, so we learned we learned a few concepts. One is we learned about exploration versus exploitation. Right? That good strategies don't take extreme positions. They take a balance of exploration and exploitation. Right? The second thing we learned is the concept of breadth first search and depth first search. And along it, at the tail end of it, it's if your goal is to go and find a flower bed and you're the bee, in either the breadth first search or the depth first search, you may end up with basically desert, sand, right? And you know, flowers don't grow on sand, so the bee now backtracks, quite literally backtracks, isn't it? Looking, because it knows that now that was a bad idea. I'm outside the forest completely. That's all it is. So these ideas were obviously developed long ago, very simple ideas. Now with these ideas, just look at this picture again. Now, do you see something, some flavor of that, just looking at this picture, something of that happening here? Can we use something like that? If you think of a thought, so here's the thing. Let's say that you have to think 3 stages of thoughts, right? You ask the LLM to produce thoughts repeatedly from the input. It will produce some thoughts. They are like flower beds. Some flower bed may be better than the other. You are the bee. Would you agree? Isn't it? It makes sense. And so it becomes a question of finding which flower bed is the better. And now you can take either a depth first or a breadth first approach at that particular moment, right? To go to the next thought and the next thought, right? And you can backtrack and do things like that on your own, isn't it? Now you can say, well, it is okay. I can produce these ideas, but who is going to judge it? You need somebody to tell how good those thoughts were, right? So if I were to produce 3 ideas, I might argue that all of them are brilliant and better than any idea anybody could ever come up with. Is that possible? I'm posing a question. If I produce 3 different thoughts, I could possibly argue all of them are correct, isn't it? It's a trick question. So why would I produce multiple thoughts and then I need to still figure out which thought is right? Who would I go to ask which is the best thought amongst these? Or which one looks most worth exploiting? Which is the best flower bed here? And who is the subject matter expert? Yeah, you could theoretically bring another agent in, but what happens is, here's a bit of an asymmetry in LLM, which is the last piece of the puzzle for this paper. See, this in machine learning, it has always been true in a broad sense. that generative models are much harder to build than evaluative or discriminative models. Right. Which is why classifiers, regressors have been there for a very, very long time. Much of the generative work is of much more recent vintage. So, in particular, it's true with the LLMs. When you ask the LLMs, they're actually weaker, even though they are the king of the hill for generative AI these days. They actually are relatively weaker at generation than discriminators or evaluators. So they can generate something, but you turn around and you ask, okay, now you score and you evaluate between these three, right? And they will shine. They're very good critiques. So what you could do is you don't even have to go to another agent. You can repurpose the same LLM and now ask, okay, why don't you go and score it? Your thoughts. You see that, right? You exploit the asymmetry in its generative versus evaluative or discriminative ability. Right? And when you put all that thing together, you now is the whole thing beginning to sing now? Can you guess what this paper will do?
A-star search for all the answers.
What's that?
A-star search for all the answers.
Exactly. And so this is it. It will.
I'll ask you one question.
Sir,
Sorry, somebody is saying that.
Go ahead.
yeah, whoever's saying that, sorry, I jumped on you. So please go right ahead. I'll take my
That's
next.
Krishnan. That's Krishnan.
Okay, so let me go. So in practical applications, Asif, so you can potentially have some criteria for success, right? I know critics, LLM critics can be used to judge whether which output is good enough. But in some applications, can we have a criteria?
Yes, very good thought, Krishnan. Hold that thought. See, at this moment, we are not gone to the output. At this moment, you are still at step one. And all you are asking is, which of these is the best step one? Because there is no objective way. The objective answer is here. This one you can tell whether it solved the puzzle. For example, if it's a puzzle, whether it solved the puzzle correctly or not. Whether Mary has 23 apples or 42 apples or whatever it is. That you can objectively tell, but how do you judge a thought? It's just a step in the thinking process. And so at this moment, you're asking the LLM just to judge which of these is, to give a score to each of the thoughts that it itself produced, right? To wear a different hat and to score itself, right? Madhu, your question?
Yeah, Asif, you did bring up the discriminatory and generative. So would you mind just giving a 1 minute recap of what that is that goes together in here while we are touching this topic?
Yeah, in a way, scoring. See, whenever you score whenever you ask a machine to score something, right? It is basically in some sense, a regression problem. You're saying, given this thought, what score, what number would you associate to the goodness? Right? And regression is a discriminative. Remember, what is it? Okay, let me write it in mathematical notation.
Yeah, in the sense of the probability. So,
probability y given x.
Yeah,
That's
exactly.
what it's a conditioned on x. Whenever you produce all predictive models are in a way discriminative models, right? Of this form. So this is it. This is it. You're asking it to score, produce a number here for each of these thoughts. And so using that, you produce more thoughts. But now something bad can happen. Sometimes look at this path, and this path is the interesting path I want to talk about. Look at this path. What happened? You start with a reasonably good idea. So in the beginning, you start with 3 ideas. One idea turned out to be a bad one. So you kept 2 ideas, the 2 green ones, the left and the middle one. But if you pursue the left idea, it led to another good enough idea in the second thought, but actually a roadblock on the third one, isn't it? A really bad third step. So, right, you realize that one can backtrack from that potentially, isn't it? And then one can come to this idea, then go to this idea, and so on and so forth. There is a way to backtrack efficiently and make progress. What is the virtue of this compared to the COT with self-consistency? See, COT will go on producing complete chains with outcomes and then take a vote amongst these. And it is possible that none of them may be right. Right? On the other hand, here at each stage, you do two things. You prune out some bad ideas. And you move forward with a limited set of good ideas, good thoughts that you propagate to the next stage. Are we making sense? That is the gist of it. So if you got that, then the rest of it is...
Asif, but doesn't that mean that there's a major difference between chain of thought and tree of thought? If you do the early pruning in tree of thought...
Absolutely. Yeah, it is. It is no more chain of thought. It is a tree of thought. With all of the, you realize that the moment you make it a tree of thought, it is now really a balance between exploration and exploitation.
Okay, perfect. Thanks.
So is this something that I'm sure you're going to cover how part, and I know you're touching the input part here. I don't mean to jump my gun too quick. So you're going to talk about how this happens.
We'll talk about it.
Okay, got it.
See, there's no mystery to it. You ask it to produce a thought. Like, for example, chain of thought, what does it do? It produces three thoughts. Right? It produces the first thought. So let's take it this way. Let's say that the input is X, right? You produce the thought T1. And then, having produced X and T1, you ask it to take X and T1 together to produce T2, right? And having produced T2, you ask it to produce a T3 after having looked at X, T1, T2, and T3. And then, having looked at all of this, you're supposed to produce the outcome, right? Now, you can ask this question, what is a thought? Like, how does it differ from a token? Because that's what ultimately LLMs produce the next token based on the previous. So the definition is, a thought is a more coarse-grained view. It's a bag of tokens, right? Let's say one full sentence or something like that. One way to look at it is produce one whole sentence. Are we making sense? You can define your thought like that. Right? And then you produce the next thought and the next.
So can you do a demarcation on the thought where it says that it cannot cross some boundaries, not at a sentence, but at a notion boundary or
you can do
boundary?
that. It's up to you. It's up to you. In fact, that's what we'll see in the examples. The creative writing, that's literally how it will proceed. Yeah. It will create one paragraph maybe, and then you say, okay, after that, that one paragraph is one thought. Yeah. It is up to you. See, we are talking at the level of abstract mathematical concepts. But what is your thought is your choice to decide.
Asif, I have a question. Sorry. Okay, yeah. So the idea here is to get to a deterministic solution or close enough to deterministic solution for every time we try to do this. Is that something? I mean, because the way Gen AI is, and are we like trying to like see how we can? I mean, these processes are all like driving us towards that. But my question is like, do you have like not just in algorithms alone, but in terms of compute and what is a feasible, I mean, like cost-effective, feasible ones when it comes to doing these things? Can you touch upon that as well when you're doing this?
Yeah, definitely. The best way to, so yeah, that is something I will talk about, but I'll give you the answer. See, first of all, LLMs inherently are non-deterministic. The moment you start sampling off the softmax, you have thrown determinism out of the window, right? Now the thing is, how do you ask questions that have exactly one answer and get it right? These are means to do that. You're taking a language engine and you're trying to do math with it, for example, or crosswords with it, right? For language engines, it is hard. Language models, it is hard. Right? You're trying to somehow guide it to the right answer. Whenever you do it, you of course pay in computation. So as you go in this diagram from A to B to C to D, you realize that more and more and more is happening. And so the computational cost is increasing. Yeah. Inference cost is increasing. That's a given. But when you need a precise answer, like for example, if the IRS uses it to determine how much to tax you, you don't want a non-deterministic machine sitting there, right? Essentially flipping coins.
Also,
So-
another thing is repeatability. Also, I mean, again, deterministic sort of plays around that. My thing is, the thing is like, how to get to accurate answer, especially when it is math is involved. But is the repeatability aspect of it is also another one, right? So, and that's another. I mean,
See, the right way to do that is there are multiple ways to do that. See, if you remember in that paper, alpha geometry, for example, we said, right, that LLM can throw in a point, but a solver can determine whether the solution, with that, it can solve the problem. Because there's a deterministic machine that eventually says it is correct, makes a difference. Likewise, with the paper, the math breakthrough paper, what was that called? I forgot the name of the paper. Where Fun search, yes, fun search. Once again, there was a deterministic machine. There was a validation step. So somewhere in there, you have to throw a deterministic machine if you want to be absolutely sure. Yeah. So see, the value of papers like this is not to give you a machine which is really perfect at situations where you produce deterministic answer, but it is saying that, see guys, this technique can solve such hard problems where you need deterministic answers much better than other techniques. Therefore, for normal situations where the constraints may be relaxed, occasionally different answers are okay, so long as it is in the neighborhood of the right answer, it's fine. Then, for example, in creative writing, this is a really good approach to apply.
Yeah. So if everything becomes deterministic, especially in the machine learning way, I mean, what's the differentiation it's going to be with the algorithms, actual, programming that we know it's going to work the way we write it versus
Madhu, there's a subtle difference to it. See, a probabilistic machine and a deterministic machine, these are two different words. For example, given the data, given the same data set, especially if the algorithm supports if it supports a convex loss surface, it will produce a model that predicts for any given input a value. It's a probabilistic machine, but that machine is deterministic because at its optimal training, given the same data, it will every single time produce the same answer. Given the input, it is deterministic in that sense. While being probabilistic, it is still deterministic. But the moment you start sampling of the softmax, for example, in an LLM, then it is both probabilistic and non-deterministic. So that's the nuance there.
right. Sounds good.
Sir, in C, why chain of thoughts, why they don't self-terminate itself?
But they do self-terminate themselves.
So then what is the difference between D and C then?
No, between D and C, the difference is that in D, at each stage, you search for the optimal thought. Whereas in C, you may reach the solution using some pretty poor arguments also. Or you may not solve. See, the risk with C is there's a higher probability that the majority vote will be wrong. Right? You may not have hit upon the solution because you're saying, let 100 solutions get generated, I'll just take the vote. Okay, guys, so we are still on figure 1. I'll just go through now with the rest of the paper, and you should find the paper hopefully easy to read. I will deliberately go over only the key ideas. So see, this is a key. Where did I leave my mark? So chain of thought prompting is, you realize that it's complete exploitation. You take a path and you just go straight to it. The bee doesn't look back, right? So that's that. On the other hand, sample sequence, so is a continuous language sequence and so forth. I won't leave that. here the main point they make is, see, there is no local exploration of different thought steps, right? In this self-consistency, right? If you have thought, let me use a different color to illustrate this. What could it be? If you have thought this thought or this thought, you think only one more thought, isn't it? Because COT with self-consistency is just lots of COTs. You think one thought forward. What is your next thought? And so you're not leaving the possibility of exploring a few more thoughts, right? So it is never the opportunity to explore. That's the main point they're making. And now comes a very interesting statement from a great guy. I believe it's really old. I believe it's 1957 when Neville wrote this problem. This statement in a paper. He said in the first, I suppose, when AI was just taking off, the classical AI, he said, a genuine problem-solving process involves the repeated use of available information to initiate exploration, right? Which discloses in turn more information until a way to attain the solution is finally discovered. Right? So, and if you go back to look at the bees, I have a whole hive of bees. Right now, given 3 flower beds, what should be the optimal distribution of the bees here, here, here? Right? How many bees should go here? How many should go here? How many should go here? So you get the most honey. You can do it only if you search the whole solution space, the problem space. What he calls it the problem space or solution space? One of them. But it's the same thing. So now this statement is important. And then I will just read this one part because to me, this was telling that actually we do it in the same way. Research on human problem solving suggests, from cognitive research, suggests that people search through a combinatorial process, problem space, a tree where the nodes represent partial solution. We solve it. We have many partial solutions, and then we think what to do next. And the branches correspond to operators that modify them. Right? Then we say, okay, what can we do with this? What can we do with this? Isn't it? So I can give you an example. Somebody says, what will happen? Like we have to work out some fluid dynamic equation. So what do? You do like, actually, is that a good example? Yeah. So there are many problems for which there are not many good solutions. So you will come up with many hypotheses. Let's take this approach. We will use this perturbation theory. We will hypothesize that this is the function. We'll hypothesize that this is the function. Right? And then you go to the next step and soon you hit a roadblock and then you start coming back. But you have multiple hypotheses. Isn't it? So one example that someone gave is, suppose that I saw somewhere, suppose I ask you this question that what's a non-consumable? I mean, one obvious thing is finding your destination through a maze. Right? It makes sense to explore multiple paths and make progress, but that's too easy. That's too academic. One example I saw somewhere was this. Suppose you go for an interview. There are multiple strategies that you can take when you interview. In our technical world, you know how it goes. There's the behavioral interview. There's a technical round. There is thing. Now, when you go for an interview, you can take multiple. Like assuming that you're really smart, you want the job. You know that you can easily do it. You are asked some questions. Let's say that the questions are very easy, right? Then what should be your strategy? Can be multiple strategies. You can quickly answer the questions and show the answer. Right? You could take your time, spend a lot of time giving very detailed step-by-step approach to the solution, right? But still look confident. You could look lost, right? Because you're trying to minimize the number of questions you are asked, and you know when the interview will be over, then quickly you sort of magically find the answers and put it there. to the questions, and so on and so forth. So now the question is, which is the best strategy? Right. See, you can argue for each. Then what you do? So now, let's say the LLM has come up with 3 strategies. You can do this. Then what? Let's do the evaluation part. So 3 parts are there. Right? Now you can do the evaluation part. You can make the same LLM a scorer. Right. Score each of the approaches. Then it will say pros and cons. So let us pretend to be the LLM. If you were to do the pros and cons, quickly just put the answer down and have a smug look on your face. What are the pros and cons of that in an interview process? Anyone?
You're guessing or you just got the answer from something.
That could be it. Like, somebody, guys, pretend to be LLMs. I mean, you have all been through the interview process, and you have taken interviews and you have given interviews. What happens quite often, if somebody looks at the problem, quickly writes down the answer and looks at you, yeah, it gives you a smug look.
That means your question is stupid. No?
You're not demonstrating the approach to the problem solving.
Yeah. One con is that your first reaction is, oh gosh, this guy has really practiced on lead code.
Yes.
Right? And knows this problem. Isn't it? Or has seen this problem because somebody has in the company, some insider has given this answers to that. You think of a lot of things, and even if you give him the benefit of the doubt that he has solved it, there is a risk that you don't like a smug face, smug look.
Right. It can be the guy is really brilliant.
That also, so that's the upside. That's the pro of it, right? So positive score, it could be a good strategy because you may be dazzled by the brilliance and say, okay, interview over, I'm taking you. It could be that you feel threatened. It could be that you feel you come up with a negative interpretation that, oh gosh. No, sometimes you feel that he has seen this problem. A more plausible answer is you may feel he has seen this answer.
Or maybe he thinks your question is stupid, right?
Yeah.
You give me a
Or
stupid
something
question,
like
hey,
okay. So that is, see, what are we doing? We are thinking like the LLM. What about the second approach? Methodically think through all of them, take all the time to show all the steps, give the correct answer, take the time. That's approach number 2. And approach number 3 is just actually look lost. And then towards the end.
Student office hours.
So you guys see that, right? That each of these stages can have. Now, no one answer is correct, right? No one answer is correct. There's a probability that to look brilliant was the right approach. There's a probability that now what happens is, oh, hey, Albert, could you please get going? You know what I'm talking about. Yeah. Or you could, one of you, please. So there is so how would you know the next questions that come from the interviewer? Yeah, we are on the way. We'll be there in 15 minutes.
Yeah, sure. So because
Okay.
Right.
Right. So if you go to the next question, let's say that you took the approach of looking brilliant, and you go to the next question and you see a little bit of a masked anger or a flushed face on the other end. What should you do at that particular moment? You should backtrack and change your strategy. Right? Look confused and then take your time to answer the question. Right? So that is all that this tree of thought is saying. And if you think about it, you do it. Consciously or unconsciously, you do it. Right? Isn't it in real life situations? That's it. That is it. Are we making sense? That is it. That's all I would say. So there is a thought generator. There is a thought evaluator. Make sense? Generator is the same LLM. Yeah.
To me, it appears the thought generator and creating the tree is the most.
That is the main thing. Yeah. And unless you have a scorer, how would you move forward? How would you eliminate? How would you prune the tree and go towards the solution? And then the depth first and breadth first is, yeah, there's a mechanics, internal details. It turns out that for some class of problems, number problems, the breadth first search does better. For some other problems, depth first search does better. But if you know all of this, it's there. But the important thing is that See, one of the problems is this game of 24, right? Given a set of numbers, you have to add them to, you have to put mathematical operators so that they evaluate to 24, right? So let's look at this picture a little bit carefully. What is the chain of thought? Do you notice that you could look at this number for, let me put this number in bold, sorry, no, big letters, 4, 9, 10, 13, right? So you could take the path, one thought could be, hey, let me put 4 plus 9. First step. You put one operator there, that's step 1. You realize that you can put only 3 operators in between them. So it's a 3-step problem. It's a simple 3-step problem. So you decide that plus is what goes here. You put plus here. That's one answer. The other one is you decided to do 10 minus 4. The other one, right? Now what happens with this? The evaluator will come and think, oh, it comes to 13. And so now if 4 plus 9 is gone, I'm left with 10, 13, and 13. Right? If these two become plus, now I have 13, 10, 13. There is, it's too big. There is no way I can make it to 24 now. You see that, right? Yeah. It gets a little harder to get to 13. So then you can say, okay, I abandoned, let's backtrack from this. Here, this has a high score. So I get to 6, and then I say, okay, now I have 6, 10, 13. Right? Now, what do I do? 10 minus 6 went away, so 9 is still there. 9 is still there. Okay. So now I can say, okay, I have to get to 24. What can I do? I can do, well, it decides to do this. It could decide to do this. You know, from this good step, it may do 13 minus 6 to come up with 7, and that takes it to a bad solution. So it literally can be scoring itself and making its way to a good solution. So you literally see it in action. You see it, guys, step by step. It's trying to reason through. Evaluator is reasoning through and scoring the solution. Yeah. And these results make it clear. So I will just do one example. The results make it clear. What is the success rate? With just input output, the best blue does pretty badly. It never gets more than 25% of the time right. The chain of thought does, we consider Euclid setup like success rate using best of k samples, like k times the sample, you do it. So you notice that the success rate of this saturates at about 45%. But that seems to be the place where the tree of thought practically begins. You notice that the tree of thought, it has a way higher success rate. Right? So I suppose the results speak for themselves. This argument, this thing works basically, right? And you can see, compared to the chain of thought, for example, samples failed at each step, you can see those numbers are drastically different, right? Creative writing also produces a similar result. So now the trouble with creative writing is, how do you score? You use ChatGPT to score, GPT-4 to score it. The final output, who has the right output and better output or something.
Fine, is it critique you're saying?
Critique, yeah, sort of. To evaluate the final thing. Yeah.
In that regard, should it be in the same family of models, or can we use something like Llama 2?
No, it can be in a different one. So usually you bring in a much bigger model to say, okay, what is going on? So that is,
Asif sir,
yes.
isn't this similar to QStar?
You mean A star? No? A star.
Yeah, so OpenAI have announced this Q learning algorithm, QStar.
Q learning. Okay.
Yeah.
How about this? We park the idea of Q learning. I'll cover it properly better. But there is a little vague similarity, but this is a very specific thing. But yes, see, whether you look at Q learning or all of this, A star and all of these, there is overlap between these ideas. There is overlap. Yeah? But they are different ideas.
Sure. Thank you.
But that's a good observation, though. It's a good observation. All right, guys. So I leave you to study the rest of the paper carefully and then take the quiz. Guys, please do. So now I would request you this. I'm going to do the instructor. I'll walk through the instructor framework after lunch, but please, through the lunch, take the simulacra and the tree of thought quiz. As you do the quiz, perfectly okay. You read through the paper and you go back and forth and search for answers. But hopefully it will be an aid for you to study the paper much more carefully. But do it, guys. These in our field are key concepts. Right? It's an emerging, fast-moving field, and these are key ideas. This is where the state of the art is, or close to the state of the art is. It's worth knowing these big ideas. I'll stop with that. And